Hello everyone, let us see the working of Maxwell Bridge in this video. A Maxwell inductance capacitance bridge, also known as Maxwell Bridge, is a modified version of a Wheatstone bridge which is used to measure the self-inductance of a circuit. A Maxwell bridge uses the null deflection method, also known as the bridge method, to calculate an unknown inductance in a circuit. When the calibrated components are a parallel capacitor and resistor, the bridge is known as a Maxwell-Vane bridge. The working principle is that the positive phase angle of an inductive impedance can be compensated by the negative phase angle of a capacitive impedance when put in the opposite arm and the circuit is at resonance, that is, no potential difference across the detector and hence no current flowing through it. The unknown inductance then becomes known in terms of this capacitance. So this is the circuit diagram of a Maxwell bridge. So we have R1, I1, the resistors and inductors here, R3, R4 and R2, the four arms of a circuit. Okay. An AC bridge consists of a source, a balance detector and four arms. In AC bridges, all four arms contain an impedance. Okay. The AC bridges are formed by replacing the DC battery with a AC source. That is why we represent it as here. So these are very highly useful to find the inductance, capacitance, storage factor, dissipation factor and etc. So let us see the bridge balance circuit. So here if we see, we can see four arms of the bridge. So now at balance condition, the potential difference between this point B and D must be 0. From this, when the voltage drop from A to D equals to drop from A to D both in magnitude and phase. Now at this condition, E1 will be equal to E2. So now we have from this figure E1 will be equal to E2 under balance condition. So Z1 equals to I1 into I2 into Z2 and I1 equals to I2 is equal to E by Z1 plus Z3 and I2 equals to I4 which is equal to E by Z2 plus Z4. So from this equations we have Z1 Z4 which is equal to Z2 Z3 and when impedances are replaced by admittance we have instead of Z we represent it as Y. So Y1 Y4 which is equal to Y2 Y3. Now let us consider the basic form of an AC bridge. Now let us see the derivations. So as seen here under balance condition we have I1 equals to I2 and I2 equals to I4. Now when you equate the real and imaginary parts we get R1 which is equal to R3 by R4 into R2 and L1 which is equal to R3 by R4 into L2. So we get the resistances as well as the inductances. So the main points to be concluded are we get two balanced equations that are obtained by equating real and imaginary parts. This means for an AC bridge both the relation that is magnitude and phase must be satisfied at the same time. Both the equations are said to be independent if and only if both equations contain a single variable element. This variable can be inductor or resistor. The second main point is the equations are independent of frequency. That means we do not require exact frequency of the source voltage and also the applied source voltage waveform need not be perfectly sinusoidal. Thank you everyone for watching the video.